Well, welcome back to AP Precalculus, folks. Hello, nerds. Today we are going to start and actually finish Unit 2.3, Exponential Functions. A very special type of exponential function, though. We're specifically only talking about exponential growth and decay functions today. There are other types of exponential functions, but today we're only talking about growth and decay functions, very specifically, okay? While exploring linear growth, we observed a constant rate of change. You might recall back to arithmetic sequences, the common difference, and then they could be modeled with linear equations, where the slope and the common difference both tell us how the output will change as the input changes. So here we have a slope of 2. So that tells us our outputs will go up by 2, y values, as our inputs, x values, go up by 1. But in our lesson today, we're going to be, for the first time ever, because you did it in Algebra 2, exploring what it means to grow exponentially or decay exponentially. We're going to look at some real-world scenarios. At the very, very end, we'll talk about a word problem, and we can have a percent change of time instead of something that is constant or linear. All right. Definition of an exponential function. Specifically, an exponential growth or decay function. Not all exponential functions have these properties. This is specific to growth and decay. In fact, this is definitions of growth and decay functions. An exponential growth or decay function in terms of x is a function that can be written like this. A times b to the x, where a and b are both constant values. They are not variables. X is the variable. So what makes it an exponential is that the variable is the exponent. Okay? If the variable is not the exponent, if the variable is the base, like x squared or x to the third, that's a power function. When you make your variable the exponent, it's an exponential. And if it's in the form a times b to the x, then it is exponential growth or exponential decay. However, specifically, b, your exponential base, must be a positive number. Your exponential base can never be 0, because if it was 0, the whole thing would be 0. And your exponential base can never be negative. Why, Mr. Rep? Because your exponent, x, can take on any number at once. So let's just say the base was -1/2 or -2, anything negative, and I said, okay, now raise that to the 1/2 power. What I just asked you to do is take the square root of a negative number, which results in an imaginary result, therefore not graphable in the real number system. And that is why our exponential base must always be positive. Your a value on the front, which if you think transformations represents your vertical stretches and shrinks, it's just faster to say vertical dilations, it cannot be 0. Because if a was 0, then once again your whole function would just be 0 and you wouldn't have anything exponential. I kind of already hinted at this when I said that the exponent could take on any value at once, but the domain of all exponential functions, not just growth and decay, the domain of all exponential functions is all real numbers. You can raise a positive number to any power you'd like. But when you raise a positive number to a power, what kind of result is always guaranteed? A positive number raised to any power, what kind of result is always guaranteed? Positive. That's going to have domain implications, range implications in a moment. I would like for you to scribble this out, because it is not true where it's written. So scribble that part out. It'll get rewritten somewhere else where it's more true. The constant value a that sits on the front is known as your initial value. And the reason why it's known as the initial value is because if you use x equals 0, you end up with a b to the 0 power. But what is b to the 0, regardless of what b equals? 1. All b to the 0's here equal 1. So you're left with a times 1, which is just a. So a is going to be our initial value. And let's talk about the graph for a moment. If you use x equals 0, where are you on any graph? The y-intercept. So the initial value of an exponential growth or decay function is also going to be your y-intercept, because it's always going to occur when x is 0. So, we're just stitching ideas together. All right, the thing I scribbled out is about to come up. As long as a is positive, and by the way, in order for it to be called an exponential growth or decay function, a must be positive. So again, it's not characteristics of exponential functions, it's specifically exponential growth or decay functions. A must be positive. If a is negative, you do still have a function, and it is still exponential in nature, but it won't be called a growth or a decay function anymore. It'll just be an exponential function of some generic sort, okay? So either way, you must have a be a positive number. But b can take on one of two different situations. B is either a number larger than 1, or it's a number between 0 and 1. Remember, b has to be positive. So if b is larger than 1, you are multiplying by a number bigger than 1 over and over and over again, which is exponential growth. And if you have exponential growth, then you would say b is, yes, b can be any number larger than 1, including decimals. The rule is b must be a positive number, so yes. It has to be greater than 0, so it's either between 0 and 1 or greater than 1. It can't be exactly 1, and the reason why is because if b was 1, you could raise it to any power you want, and you're just going to get 1 over and over and over and over again, which means you actually just have f of x equals a, which is a horizontal line, so it's not exponential. Yes, right here, which is what it says. Yep, b has to be greater than 0, but it can't be 1. So b is called your growth factor if it's greater than 1. That's why I said it doesn't belong there. That's why I scribbled it out. Because if b is between 0 and 1, then it's not growth. It's decay, exponential decay, and b is your decay factor. There. And now for a while, we're just going to do algebra 2. We have y equals 2 to the x. And we're going to use the x values -2 through +3 so we can plot them, and then we'll connect the dots. You see, the major difference between exponential functions and geometric sequences is that our input values, our domain now, can be any real number. So we can connect our dots with a line. Where when you're talking about sequences, you had to say the first term, the second term, the third term. There was no value in between. Alrighty, this says 2 to the -2, 2 to the -1, 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3. Just showing you how you would get these things. Again, this is just algebra 2. But 2 to the -2 is the same as 1 over 2 squared, 1 over 4. 2 to the -1 is 1 over 2. Any positive number to the 0 is 1. And then from there, it's just exponents. Hey, look at these numbers. They represent a geometric sequence. What is the common ratio? 2. Ta-da! Yeah, it's right there. And what is your a value? A is 1 in this term, in this case. Because it's 1 times 2 to the x. Let's plot these dots, and then we'll fill out the stuff on the left, okay? Be careful. Your x's and your y's count by 1s, but your y values can come out as fractions. Oh, so let's see. When x is -2, we have y as 1/4. That's way down here. And then at -1, we have 1/2. At 0, we have our a value of 1. 1 jumps up to 2. 2 jumps up to 4. 3 pops up to 8. And if you wanted to, 4 goes all the way up to 16. Look at this thing. But we've already said a positive number raised to any power is always going to be a positive result. That means it doesn't matter how far left I go, I'm never going to hit that x-axis. Ooh. Let me do my best to draw a curve here that hits these dots. Whoa, got a little wavy there at the end. Sorry. There we go. Now on my paper, I took the time to turn the paper sideways and then write not vertical. This is not a vertical asymptote. It just has a really, really steep rate of change. But you know what happened? Ashley mumbled it a second ago. Because it's always going to be positive, we have a horizontal asymptote. And exponential functions, all exponential functions, not just growth and decay functions, will never hit their horizontal asymptote. Never. Now, rational functions, you saw, they dance all over their horizontal asymptotes all the time. Exponentials, that'll never occur. So what was our domain? We've already said it. You plug in any number you want. Domain, all real numbers. But the range for this one is only positive values. So from 0 to infinity, not including 0. As x heads towards positive infinity, that means as x goes to the right, what is my y value approaching? Infinity, because it's going up. But this is not AP language. Let's write it in AP language. The limit as x approaches infinity of f of x equals infinity. That's better. And you can see my purple curve. As x goes to the far left, my y values are going to head towards 0, the horizontal asymptote. So the limit as x approaches negative infinity of f of x is 0. The definition of a horizontal asymptote. The limit as x heads towards one of the infinities equals a number. That is the true definition of a horizontal asymptote. The only asymptote we have is the horizontal one. And because my horizontal asymptote is the x-axis and no exponential can ever encounter its horizontal asymptote, we do not have an x-intercept. We only have a y-intercept, the initial value. And what kind of concavity does this have? Is this concave up or down? It is concave up. Let me remind you what that means. That means the second differences, or you could say the rate of change of the rate of change, is positive. Or you could say the rate of change is increasing. So it can be said a lot of different ways. Speaking of second and first differences and all that stuff, it's not in these notes, and I haven't really looked forward yet to see if it's in further notes. But I wanted to talk about first differences for exponentials. When we were working with polynomials and I gave you tables of data, you were forced to use first, second, third differences, so on and so forth, in order to identify the degree of the polynomial, right? And once you found a difference type, first, second, third, worst case scenario, fourth, that stopped changing and was a constant value each time, you found the degree of your polynomial. And that's how you knew it was a polynomial in nature. If I give you a table of data and say use differences to determine a model, something really neat happens. I'm saying something really important here. The first differences of exponentials are always a geometric sequence. For example, let's look at the first differences here. Plus 1/4, plus 1/2, plus 1, plus 2, plus 4. Now you might be saying, duh, that was just these numbers just shifted over slightly, right? And they go, well, yeah, but that was only true because this was specifically an exponential growth function. What if it was just an exponential function, meaning I allowed there to be shifting? If I wrote -1 right here, right there, you'd have -3/4, -1/2, 0, 1, 3, 7, which would no longer have the pattern of ×2. But the first differences would show you the pattern of ×2 each time. Once again, all exponential functions have a property that their first differences are a geometric sequence, which is why we learn about geometric sequences before we talk about exponential functions, because that's how you identify them using a table of data. And I'm hoping that'll show up in a later lesson. If not, I'll have to do some more addendum stuff. So just looking at these real quick, we're saying, are they exponential, yes or no? Well, initial value always means that x equals 0. And in order for it to be an exponential, the base must be a constant number, and the exponent must be the variable. So here, what is my initial value? What do I get when x is 0? You get 1. There it is, because 2 to the 0 is 1. What is the base here? It is 2. So is this exponential? Yes, it is. In fact, it's exponential growth, because it can be written in the format y equals a times b to the x. We're here, like it was before. A is 1. And the growth factor is 2. Let's be really clear here, in case you try to interchange the words. The growth factor is not the same thing as the growth rate. Rates are something different. Okay? This one. If you use x equals 0, do you get 0? What do negative exponents mean again? It goes under the fraction. So this is actually 4 over x to the third. So when you try to use x equals 0, what do you get? Undefined. Its base is actually x. That can't be. No, that is not an exponential function. Why? Because it's a rational function. That's why. That's a rational function. That's not exponential. If you use x equals 0 here, you get 5 times e to the 0. But what is e to the 0? 1. Yeah, 5 times 1 is then 5. And the exponential base here is e, which is a number. It's about 2.718-ish. If you would like more information about the natural base e, I invite you to go to YouTube and look up the history of the natural base e. Okay? We don't have time for that right now. It was not created. It was discovered. Yada, yada, yada. So is this an exponential growth or decay function? Yeah, it is. Because it's in this format. You can see A is 5. And the last one. It doesn't even have an x. So what is its initial value? It's this. That's your initial value. It doesn't even have a base. So no, this is not an exponential function. You know what it is? It's a constant function. Because 3 is a number, 4 is a number, and e is a number. Squiggly x means approximately. I grabbed a calculator. It's almost 130. But it's a straight line. Okay. Easy peasy, right? You can identify exponential function, growth and decay functions, no problem. Scoot. Let's be really clear here. This is no longer an exponential growth or decay function because there is a horizontal shift. It is an exponential function, but it is not a growth or decay function. That kind of language is specific to a b to the x. Okay? Just wanted to throw that out there. Anyway, we are going to find the exact value of f of 2. Two plus 1 is 3. PIMDAS says exponents come first. 3 times 3 times 3 is 27. And it says no calculator, so instead of saying 6 times 27, let's do 6 times 20 and 6 times 7. 6 times 20 is 120. 6 times 7 is 42. 120 and 42 makes 162. You know what? Because it's going to come up in a minute. This is an exponent. Do you guys remember under what circumstances, if you could think back to Algebra 1 and Algebra 2 for me, under what circumstances do we add exponents? What causes us to do that? Multiplying what? When you're multiplying things with the same base, you add exponents. You know what? I'm just going to write this up above here. So if I say 3 to the x plus 1, that means I multiplied a 3 to the x and a 3 to the 1. Can we agree to that? But isn't 3 to the 1 just 3? Wait a minute. That right here, 6 times 3 to the x, that's an exponential growth function. And that's a vertical stretch. Also known as a vertical dilation. You know what's really neat here? This horizontal shift was the same as a vertical dilation for an exponential function. How neat. Okay, let's do this again. You don't have to write neat if you don't want to. Whatever, I don't care. Nah, he's back there talking crap. In order to pull this off, you'd have to think back to Algebra 2 and tell me what the 1/3 power means. Cube root, cube root. And the cube root of 8 is 2. There it is. Again, because there's a negative sign here, this is neither exponential growth or decay function. It's just an exponential function. All right? There's no way for me to manipulate that one like I could this one. That one's stuck. How about let's write our own exponential growth or decay function. What we have is initial value of 3, and the output value doubles at every 1 unit increase of the input value. That literally means times 2. So 6, 12, 24, 48. We can already see that A is 3, and bless you, the base of the exponential is 2. Because there was no vertical shifting, we don't even need to go to the first differences to see that this is a geometric sequence. And the common ratio is the exponential base. If there was a vertical shift, these numbers would not be a geometric sequence, but their first difference would be, and the common ratio would have been 2. Either way, what we get here is g of x equals initial value times exponential base to the x. Easy enough. Exponential growth and decay functions will be easy to find their equations because there's no vertical shifting. Can I flip? Flip them. What in the world? All right, here we have 2 different exponential growth or decay tables. Awesome. And how do I recognize them as growth or decay tables? Because the y values form a geometric sequence. That's how I recognize it. Let's do blue. Let's do purple and green. Purple. What am I doing at each step? Multiplying by 2. That means my exponential base is 2. My growth factor is 2. My initial value is what I'm going to get when x is 0. So f of x, and this is growing. We could see it's growing. F of x is 3 times 2 to the x. Again, there is a difference, just so you don't try to use it interchangeably yet. There is a difference between a growth factor and a growth rate. Okay? This growth factor is 2. That is not your growth rate. These numbers are getting smaller, and they do represent a geometric sequence. And we're clearly doing what to these numbers? We're dividing by 2. However, because it has to be set up as a multiplication, what are we multiplying by? 1/2. This exponential decay function will be initial value a of 5 times 1/2 to the x. That's easy, isn't it? It's so easy when there's no shifting. No, not today. No shifting today. What we actually have down here in example 6 is the graphs of both of these 2 things that we just found. Now, I'm going to be honest with you. I don't know why this is written here. I actually don't see why this is written here, but I do want to talk about it. What it's showing is if you change your x to x plus 1, remembering that multiplying two numbers of the same base makes us add our exponents, this could be written like this. But b to the 1 is just b, correct? And order of multiplication does not matter. Which you can see here is b times what the original f of x was. So what this line here is telling us is that a horizontal shift for exponential growth and decay functions, a horizontal shift is always a vertical dilation of some sort. So we don't have to say stretch or shrink, we can just say dilation. Okay? Yep, I'm going to write it right now. And this is true only for exponential growth and decay functions. Okay? It's just neat that that happens. Alrighty. Because a was a positive number and b is bigger than 1, we know f is increasing and the base b is its growth factor. We know because it's growing as x gets bigger, f of x gets bigger. And because it's exponential, we know as x gets smaller, what's my y value going to approach? 0. Because it's exponential, the domain is all real numbers. Because it's exponential, the range, and actually because it's exponential growth or decay, the range is from 0 to infinity. Because remember, if it's not growth or decay, meaning if I shifted it up or down, it's just some other exponential function, then our range will be affected by the vertical shift. But all exponential growth or decay functions have the same horizontal asymptote, the x-axis, y equals 0. So approach 0 to the left and shoot up as we go to the right. That looks like this. And be concave up. And this value, boink, was 3. It's easy, right? Okay. Now the other one, which I had in green, 5 times 1/2 to the x. Well, a is a positive number, it has to be. But because, and I don't like this, I'm going to say let's be more specific. And since b is between 0 and 1, we know our function's decreasing, and the base is the decay factor. That means the further to the right I go, and you can even look at this, the smaller these y values get. But we know they have to stay positive. So it's going to approach, but never actually get there. What? What y value? 0. Yeah. But as you go to the left, well, I mean, these numbers are getting big, 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 big. So domain, like all exponentials, is all real numbers. Range, like all exponential growth and decay functions, is all positive numbers, 0 to infinity. Of course, a vertical shift would change that range, but that would only be called no longer be called a growth or decay function. And your asymptote, because it is a growth or decay function, has not been affected. It is the x-axis, y equals 0. This says get close to 0 to the right, shoot up to the left. And this was 5. Decays over time. That's not bad, is it? I mean, this is all Algebra 2, to be honest with you. Relating it to geometric sequences and talking about first differences, that's what makes it AP. And for this one, we are going to use our graphing calculators because we're going to be lazy and we don't want to have to actually compute these things. Big Tech Industries has 25 locations and is expanding by 10 new locations each year. The company growth can be represented by this function, 25 plus 10 to the x, because 25 is the initial number of stores, and then we get 10 more each year. Central Computing Inc. has 25 locations initially as well. They expand by increasing their total locations by 40% each year. That is a growth rate. The rate is a 40% growth rate. Their function is 25 times 1 plus 0.4 to the x. So for those of us that are keeping track, that is 25 times 1.4 to the x. So 1.4 is the growth factor. The growth rate is 0.4 or 40%. Okay? So now that we've said that, let's come back here. What is the growth rate? This is a 100% growth rate. So if you say 100% growth rate, that makes a growth factor of times 2. This one would be and it just so happens that it's a 50% decay rate. And the exponential base is also 1/2. That's coincidence. Because if it was a 25% decay rate, that would be 1 minus 0.25. This would have said 3/4. Okay? Anywho's it, we come here and we've typed them into our calculators in the y equals menu. Of course, I already had it done. And then you go to second table, or second graph, I should say, to read your table. Now, you all know how to read a table, so it's okay if you didn't type them yet, but there's our table. I'll even write them in blue and red because that's what's on my screen. It's going to start with 25 and then go up by 10. 35, 45, 55, 65. Now the red one, 25 stores, then 35 stores, then 49 stores. Okay, you can't have partial stores. So almost 69 stores, almost 96 stores. So I just rounded to the nearest store. Part B says to graph them. Be really careful on this one. Your x's, for some reason, go by 0.5s. Yeah, I almost messed that up the first time I was graphing it. So we start at 25. Then we go 1 to comma 35, 245, 355, 465, and 5 would go all the way up to 75. And you're going to do your best to draw a straight line. I'm not going to brag or anything, but that's pretty freaking straight. That was Big Tech. That's B of X. Now the red one, 0, 25, 1, 35. Oh, they're the same. That's neat. But then 2 goes up to almost 50. Uh-oh. 3 goes up to almost 70. Oops. Ignore that dot. 4 goes up to 96. Holy cannoli. And it would just keep going. Now I'm going to do my best to exaggerate this. These two things have the same domain and range. Red and blue makes purple. Both of them have this domain. 0 to infinity. Oops. And range? They have the same range because they both start with 25 stores. 25 to infinity. Well, when did they have the same number of stores? Yeah, when x was 0 and x was 1. And then it wants to know how many stores at 5 years. Well, B of 5 we saw in the graph was 75. But C of 5? I don't actually know. So I'm going to go back to the table. There you go. About 134 stores. Rounding to the nearest whole store. And that, ladies and gentlemen, nerds, is your Algebra 2 review for the day.